Before we open a torque converter, let us first see where it fits in the machine. The engine creates rotating power. The torque converter receives that rotation and transfers it through oil. The transmission selects forward, reverse, and the required gear ratio. Drive shafts carry the rotation to the differentials. The differentials split it to the axles, and the final drives multiply torque at the wheels. Torque means twisting force. Rim pull means the usable pushing or pulling force where the tire meets the ground. If you remember this complete path, every component in this lesson will make sense. A diesel engine cannot be bolted directly to a stationary machine through a fixed shaft. If the wheels stop while the engine remains connected solidly, the engine will stall. A torque converter solves this problem with a controlled fluid connection. The engine can keep running while the machine stands still. When the operator accelerates, the converter transfers more power. It also absorbs shock during digging, reversing, and gear changes. At low turbine speed, it can multiply torque. At higher speed, it behaves more like a fluid coupling. Some converters then apply a lockup clutch to create a direct mechanical connection. Here is the converter opened from the side. The outer cover and housing contain the oil. The impeller, also called the pump, is driven by the engine. The turbine is connected to the transmission input shaft. The stator sits between them on a one-way clutch. A lockup clutch, when fitted, connects the cover directly to the turbine. Do not confuse these parts. Engine rotation enters the impeller. Oil energy drives the turbine. The stator changes the returning oil direction. The lockup clutch is a separate friction device used only when the controller decides that a solid drive connection is suitable. The impeller is welded or bolted to the converter cover, so it turns whenever the engine turns. Its curved vanes pick up oil near the center and throw it outward by centrifugal force. This does not mean the impeller simply pushes oil straight across. The vane angle gives the oil both speed and direction. Faster impeller rotation produces more oil velocity and therefore more energy available to the turbine. If the impeller is damaged, loose, poorly supplied with oil, or aerating the oil, the whole converter becomes weak because the first step in the energy transfer is already wrong. The turbine faces the impeller but is not fixed to it. Oil leaving the impeller strikes the turbine vanes. The vanes turn the oil and the reaction rotates the turbine. The turbine hub is splined to the transmission input shaft, so turbine rotation becomes transmission input speed. When the machine is stationary in gear, the impeller may be turning while the turbine is almost stopped. When the machine accelerates, turbine speed rises. A damaged turbine hub, stripped spline, cracked vane, or incorrect converter assembly can therefore produce engine speed without believable transmission input speed. Oil leaving the turbine is traveling in a direction that would oppose the impeller if it returned unchanged. The stator catches that returning oil and redirects it so it assists the impeller. During high torque multiplication, the one-way clutch holds the stator stationary against this reaction force. As turbine speed approaches impeller speed, the return flow changes direction and the stator is allowed to freewheel. If the one-way clutch slips when it should hold, low-speed torque becomes weak. If it remains locked when it should freewheel, heat and efficiency loss increase at higher travel speed. Follow one complete oil circuit. The impeller accelerates oil outward. The moving oil crosses into the turbine and transfers energy. The turbine redirects it toward the center. The stator catches the return flow, changes its direction, and sends it back into the impeller in a helpful direction. This loop repeats continuously, many times every second. Charge oil from the transmission pump keeps the converter full, replaces leakage, removes heat through the cooler, and prevents cavitation. The converter is therefore not an isolated sealed tin of oil. It depends on correct charge pressure, oil level, oil quality, suction integrity, cooling flow, and an unrestricted outlet path. Stall means the impeller is rotating but the turbine is stopped or turning extremely slowly. This occurs briefly when a machine in gear pushes against a heavy load. The speed difference is maximum, the stator is held, and torque multiplication is high. But almost all unused engine power becomes heat in the oil. Stall is not a normal condition to hold for a long time. Continuous converter stall, riding the inching pedal, pushing against the brakes, or using the wrong gear can overheat oil, harden seals, distort plates, damage bearings, and shorten converter life. High torque at stall is useful. Prolonged stall is destructive. As the machine moves, turbine speed increases and the speed difference between impeller and turbine becomes smaller. The return oil no longer strikes the stator in the direction that needs reaction torque, so the one-way clutch lets the stator rotate. The converter is now mainly acting as a fluid coupling. Torque multiplication reduces toward approximately 1:1, although some slip remains. That slip is why a converter is smooth, but it is also an efficiency loss. The exact speed ratio and efficiency depend on the converter design, load, oil temperature, and operating point. Do not assume that every converter should show the same slip percentage. A lockup clutch removes most converter slip when conditions are suitable. The controller commands a solenoid. Oil pressure moves the lockup piston. The friction lining is clamped against the cover, mechanically linking engine side rotation to the turbine and transmission input. Engine speed and turbine speed then become almost equal, allowing only normal control tolerance. Lockup reduces heat and fuel consumption. It must release during low-speed maneuvering, major speed changes, or conditions where a fluid connection is needed. A slipping lockup clutch creates heat and friction material. A clutch that applies too early can lug the engine or cause harsh vibration. Converter descriptions can be confusing. 3-element means 1 impeller, 1 turbine, and 1 stator. 1 stage normally means the oil passes through 1 turbine in the main energy transfer stage. 1-phase designs use 1 principal operating flow arrangement. 2-phase designs change behavior as the stator transitions from reacting to freewheeling. These terms describe internal hydraulic operation. They do not mean the transmission has only 1 or 2 gears. A twin turbine or multi-stage converter uses additional turbine members for a different torque and speed characteristic, but it is less common in modern general-purpose machines. Always identify the exact converter from the manufacturer specification. Not every machine uses the same system. A basic converter and Powershift transmission are common on loaders, dozers, graders, and trucks. A lockup converter adds direct drive at suitable speeds. An impeller clutch converter can deliberately reduce converter input torque. A torque divider splits engine power between a mechanical planetary path and a converter path, often used where controlled slip and strong pushing are both required. Hydrostatic drive uses a variable pump and hydraulic motor instead of a conventional converter. Power split or continuously variable systems combine mechanical and hydraulic paths. Before troubleshooting, identify the system. The same pedal movement can control completely different hardware. The turbine output shaft drives the transmission. Inside a Powershift transmission, planetary gear sets create different ratios and directions. Hydraulic clutch packs hold or connect selected planetary members. A forward clutch plus a ratio clutch may be applied for 1 gear. Reverse uses a different directional clutch. A gear change is made by releasing 1 clutch and applying another without asking the operator to use a manual dry clutch. The transmission control valve or electronic controller sends regulated oil to the correct clutch piston. Therefore, a machine that will not move may have a converter problem, a clutch pressure problem, a control problem, or a broken mechanical path after the transmission. A planetary set contains a sun gear in the center, planet gears on a carrier, and a ring gear around them. If all members are free, the set does not provide a useful controlled ratio. A clutch can connect 1 member to an input shaft, while another clutch or brake holds a different member. The remaining member becomes the output. Changing which member is driven, held, or used as output changes speed, torque, and direction. This is why 1 transmission contains several clutch packs. Each clutch does not simply mean one gear. The control A wet Powershift clutch contains alternating friction discs and steel separator plates. Friction discs are splined to one rotating member. Steel plates are splined to another member, usually the drum. An annular piston sits behind the stack. Seals contain apply pressure. Return springs move the piston back when pressure is removed. Oil passages carry controlled pressure to the piston and cooling oil through the discs. Wet means the plates operate in transmission oil. The oil removes heat and controls friction behavior. Wrong oil, low flow, contamination, incorrect plate clearance, or damaged seals changes how quickly and how strongly the clutch engages. When the controller energizes the selected solenoid, regulated transmission oil enters the clutch passage. Pressure fills the piston cavity and moves the piston toward the plate stack. First, the piston takes up clearance. Then it squeezes the friction discs and steel plates together. Friction causes the two previously independent members to rotate as one. This is clutch engaged. More torque requires adequate clamp force, which depends on piston area and apply pressure. If pressure is low or seals leak, the plates slip. If pressure rises too quickly, engagement becomes harsh and the driveline receives a shock load. When the solenoid is de-energized or the control valve exhausts the circuit, apply pressure falls. Return springs move the piston away from the plates. The friction and steel discs separate by a very small running clearance and can rotate at different speeds. This is clutch released. Cooling oil must still remove heat and carry wear particles toward the filter. Drag can occur if plates are warped, clearance is too small, the piston does not return, or oil is excessively viscous. A dragging released clutch fights the clutch that should be applied, causing heat, poor shifts, and sometimes machine movement in neutral. Good clutch control does not jump immediately from zero to full pressure. During fill, oil moves the piston across its clearance with little torque transfer. During modulation, pressure rises progressively and the plates begin sharing torque. During full apply, pressure reaches the value needed to hold without slip. The controller may use pulse width modulation on a proportional solenoid to shape this pressure ramp. On a shift, the releasing clutch and applying clutch must be timed correctly. Too much overlap ties two ratios together. Too little overlap causes engine flare and loss of drive. Both conditions create heat and damage. Every clutch has a slightly different fill volume because of seal condition, plate clearance, oil temperature, and component tolerances. Calibration teaches the controller how long each clutch takes to fill and what current or pressure produces smooth engagement. The machine must meet the manufacturer conditions: correct oil level and temperature, reliable speed signals, correct engine speed, brakes applied as specified, and no active fault that invalidates the test. Calibration cannot repair a worn clutch, leaking seal, blocked filter, damaged solenoid, or false speed signal. A calibration failure is evidence. It is not automatically proof that the electronic controller is faulty. Inching means reducing machine travel force or travel speed with fine control while the engine continues running fast enough to supply implement hydraulics. A loader may need high engine speed to raise a full bucket but very low rim pull while approaching a truck. A forklift may need massed hydraulic speed while creeping toward a pallet. The inching pedal is therefore not simply another accelerator, and it is not always a normal brake pedal. Depending on machine design, it may reduce transmission clutch pressure, disconnect a directional clutch, modulate an impeller clutch, command hydrostatic displacement, and then apply the service brakes during the later part of pedal travel. In a clutch disconnect system, initial pedal travel operates the service brake normally. At a calibrated point, a switch or pressure sensor tells the transmission controller to release a directional clutch. Drive to the wheels is interrupted, allowing the operator to use engine power for implements without pushing through the brakes. This system is simple and protects brakes during loading work, but it may feel more like connected or disconnected than truly progressive inching. The switch position, pedal adjustment, brake pressure signal, wiring, controller logic, and directional clutch pressure must all agree. A badly adjusted switch can disconnect too early, too late, or not at all. A transmission clutch modulation system progressively reduces pressure to the active directional clutch as the pedal is pressed. At full pressure, the clutch is locked and full rim pull is available. As pressure is reduced, controlled clutch slip lowers will torque while engine speed can remain high. Near the end of travel, the clutch may be fully released and the service brakes apply. The advantage is very fine approach control. The disadvantage is that the transmission clutch itself absorbs slip energy and creates heat. Holding the pedal halfway for too long, especially under high load, can burn friction material and warp steel plates. An impeller clutch torque converter places a hydraulically controlled clutch between the engine-driven cover and the impeller. With full impeller clutch pressure, the impeller receives full engine torque and the machine has maximum rim pull. Reducing clutch pressure allows controlled slip before the converter, so less torque enters the oil circuit and less rim pull reaches the tires. Engine speed can remain high for the implement pumps. Large loaders use this principle with rim pull control. It provides excellent loading control and can reduce tire spin, but prolonged modulation still generates heat. Never call this the lockup clutch. The lockup clutch bypasses converter slip. The impeller clutch deliberately reduces converter input torque. A hydrostatic machine uses a variable displacement pump to send oil to one or more hydraulic drive motors. Pedal position or electronic control reduces pump displacement, motor torque command, or both, allowing the machine to creep while engine speed remains available for implements. There may be no conventional torque converter and no slipping Powershift directional clutch. The advantages are smooth low-speed control and easy reversing. The disadvantages include dependence on clean oil, accurate electronic control, charge pressure, and high-pressure pump and motor condition. Diagnosing it with torque converter assumptions will send the technician in the wrong direction. Identify. Some tractors, industrial vehicles, and older machines use a mechanical dry clutch between the engine and transmission. Pressing the pedal moves a release bearing and pressure plate, separating a friction disc from the flywheel. That is different from a wet Powershift clutch and different from a torque converter. A dry clutch should not be held partly engaged to control speed under heavy load because it has limited cooling. Some forklifts called clutch-type units may use a wet transmission clutch or an inching valve instead. The correct name matters. Before explaining operation or ordering parts, verify whether the machine has a dry clutch, wet clutch, converter drive, or hydrostatic drive. Think of the pedal in 4 zones, but confirm the exact machine manual. In Zone 1, the pedal is released and full drive pressure or full impeller clutch pressure is available. In Zone 2, initial travel begins reducing rim pull or directional clutch pressure. In Zone 3, travel force is very low while engine speed remains available for the bucket, blade, or mast. In Zone 4, drive is fully disconnected or reduced to minimum and the service brakes hold the machine. On some designs, braking begins earlier and overlaps modulation. A technician must measure pedal position, electronic percentage, brake pressure, and clutch or impeller pressure together to see whether the zones agree. During a truck loading approach, keep the bucket controlled and the machine square. Release the inching pedal for full rim pull while leaving the face or accelerating. As the loader approaches the truck, progressively press the pedal to reduce rim pull. Maintain the engine speed required for lift hydraulics without forcing the tires or driveline. Use the final pedal zone and service brakes to stop. Do not hold high throttle against full brakes with the drive clutch heavily slipping. Do not use inching as a footrest. The purpose is short, controlled maneuvering, not continuous travel speed control over a long distance. A conventional converter is smooth, shock-absorbing, and strong at low speed, but it creates heat and loses efficiency through slip. Lockup improves efficiency and reduces heat, but adds a piston, friction surface, solenoid, and control logic. Transmission clutch inching gives fine control, but heat is generated inside the clutch pack. Impeller clutch control preserves implement power and manages rim pull very well, but adds another clutch and pressure circuit. Hydrostatic drive gives excellent creeping and reversing, but depends on expensive precision pumps, motors, charge pressure, and clean oil. No system is best everywhere. The machine duty determines the correct design. Whenever two members transmit torque while rotating at different speeds, slip power becomes heat. In a converter, the speed difference between impeller and turbine heats the oil. In a clutch, the speed difference across the friction plates heats the plate pack. More torque, more slip speed, or more time means more heat energy. Cooling capacity can handle normal short events, not continuous abuse. Warning signs include rising transmission temperature, dark oil, burnt smell, hardened seals, glazed friction material, warped steel plates, debris in the filter, and repeated clutch fill changes. Fix the operating cause and the hydraulic cause. Changing oil alone does not remove damaged hardware. Weak drive in every gear can come from low charge pressure, aerated oil, a damaged impeller, turbine hub or stator one-way clutch, internal leakage, or a broken input path. Weak low-speed push but better high-speed travel can indicate poor stator reaction. High temperature can result from continuous stall, restricted cooler flow, low oil, lockup not applying, a stator that will not freewheel, or excessive transmission clutch slip. Engine lug or harsh vibration can occur if lockup applies at the wrong time. Noise and metal require immediate investigation. Always compare engine speed, converter output speed, pressure, temperature, and machine response under the same controlled condition. A clutch that slips after warming may have seal leakage, low pressure, worn friction material, or insufficient cooling. A harsh shift may come from excessive initial pressure, incorrect fill calibration, a sticking valve, wrong oil, or too much clutch overlap. Delayed engagement can mean an empty circuit, excessive clearance, leakage, restricted supply, or a slow solenoid. Machine creep in neutral can mean warped plates or a piston that does not release. If inching does nothing, check pedal position, switch or sensor supply, controller input, solenoid command, valve movement, and the actual pressure response. Never begin with the machine model, serial number, transmission arrangement, and correct schematic. Confirm whether the machine uses a converter, lockup clutch, impeller clutch, transmission clutch modulation, clutch disconnect, hydrostatic drive, or a dry clutch. Ask what the operator feels when the fault started, whether it changes hot versus cold, and whether all gears in both directions are affected. Inspect oil level, oil type, leaks, filter restriction, debris, harness damage, connectors, and pedal linkage. Then make a power path hypothesis. Do not jump between random components. Test the earliest point where the expected input exists but the expected output is missing. Use the manufacturer test ports and specifications. Charge pressure proves that the converter and control system receive oil. Main transmission pressure proves the common supply. Individual clutch pressure shows whether the selected circuit fills, modulates, and reaches full apply. Lockup pressure proves the hydraulic command at the piston circuit. Impeller clutch pressure should change in the correct direction as the inching pedal moves. Record pressure at low idle, high idle, neutral, each direction, selected gears, hot oil, and during pedal travel as permitted by the procedure. A commanded solenoid percentage is not proof of hydraulic pressure. Measure the result. Compare engine speed, converter output or turbine speed, transmission output speed, and ground speed. The signals must be physically believable. At stall, engine speed exists while turbine speed is near zero. During acceleration, turbine speed should rise smoothly. With lockup applied, engine and turbine speed should be nearly equal according to specification. A sudden impossible jump, unstable value, or speed with a stationary shaft suggests a sensor, wiring, air gap, target wheel, or installation problem. Before condemning a converter for slip, verify that the sensor is reading the correct rotating target and that shaft end float or target runout is not changing the air gap. A stall test loads the engine through the converter to compare maximum governed speed with the manufacturer range. It can help separate engine power, converter, and transmission problems, but it creates extreme heat. Perform it only with the correct procedure, suitable area, brakes and machine restraint confirmed, oil at the specified temperature, personnel clear, and the test time strictly limited. Stop immediately for abnormal noise, movement, or excessive temperature. Low stall speed may indicate low engine power or excessive mechanical load. High stall speed may indicate poor torque transfer or clutch slip. One number is not a complete diagnosis. Compare pressures, speeds, temperature, and all directions. A controller uses speed feedback to judge clutch engagement and fill time. If a speed sensor has the wrong air gap, a loose mount, metal on its tip, damaged wiring, or a target wheel that is misaligned or moving with shaft end float, the signal may become unstable. The controller can then fail calibration even when the clutch hardware is usable. First, graph the raw speed signal. Inspect the sensor face and target. Measure air gap and run out to specification. Check connector pin fit and shielding. Then verify clutch pressure and repeat calibration under the correct conditions. Replacing clutches or the controller without proving the signal path can create an expensive repeat failure. Imagine a loader with weak forward and reverse drive. Engine speed is correct. Charge and main pressure are both low, and every clutch pressure is low. Because all gears share the same supply, begin at oil level, suction leakage, filter restriction, pump condition, and regulator operation. Now imagine main pressure is correct, reverse is strong, but forward pressure fills slowly and drops under load. Focus on the forward solenoid, valve, piston seals, passage leakage, and clutch pack. Finally, if pressure is correct but the reported turbine speed jumps impossibly, inspect the sensor and target before removing the converter. Common inputs first, individual circuits second, mechanical removal last. The complete system is now one logical chain. The engine turns the impeller. Moving oil drives the turbine. The stator redirects return flow for torque multiplication. Lockup can create direct drive. The transmission applies selected wet clutch packs to control planetary gears. The inching pedal may disconnect or modulate a transmission clutch, modulate an impeller clutch, or command a hydrostatic drive. Pressure creates clutch force. Controlled slip provides smoothness, but excessive slip creates heat. Correct diagnosis identifies the exact system, proves oil supply, measures each clutch circuit, compares believable speed signals, and follows the power path until input is present but output is missing. That is how a technician finds the fault without guessing.